So, some of you may know Electric. Any hands? We are a sync engine. It's kind of a state transfer technology for building apps. So it's like how you move the data between the front end and the back end, which of course used to be about keeping clients and servers in sync. The challenges there are, but is increasingly nowadays about keeping humans and agents in sync, working on the same data state. And our angle at Electric is we are composable sync primitives on Postgres. So there's a whole bunch of cool ways of building apps on sync technology, but with Electric, you can do it with your stack. So your stack of choice. If you are a TypeScript developer, that could be something like TanStack, for example. And we built this TanStack DB library, which is a very cool reactive client store that's now built into TanStack. It's based on a TypeScript implementation of differential data flow. So when any data changes when it syncs into your app, everything just live queries just rerun. But it does so very, very quickly. So instead of the data changes and if maybe it's stored in a store and you rerun queries, it's a differential data flow pipeline. So everything just returns in like fractions of a millisecond. So you can have a complex app built on reactive data in the client. And you can have loads of components all making loads of live queries just on the same store. Everything renders within a single request animation frame. And then it does local instant writes using transactional optimistic mutations, where the optimistic state lifecycle is tied in with the sync machinery. So basically, this is a library that integrates sync into a mainstream application development stack like TanStack, which is awesome. And like, go check it out. There's articles on our blog, with the Electric blog, about developing TanStack and Electric. There's a really good guide to TanStack DB on this front end at Scale website. So go check it out. But if you're, say, an Elixir developer, instead of TanStack, and you build apps with Phoenix, then we also built this library called Phoenix Sync. And so Phoenix Sync is like an official sync library added into Phoenix. It works with TanStack DB out of the box in the client. It also works with LiveView, and it works through your existing Elixir app. So your plug, your router, your controllers, etc. So just to give a very quick sense of it. So this, for example, is just a standard LiveView. And if you were, say, trying to get a query result into client LiveView, LiveView ships with this stream primitive, which is basically a memory-efficient way of not having to maintain the entire collection on the server side for every client session, but still allows you to basically sync the contents of the list with the client. And so what you do with Phoenix Sync is you just swap out that stream function for sync stream, and that's it. It basically keeps the contents of the live view in sync with the contents of your Postgres database. And so LiveView does the stuff to keep your client in sync with the state on the server, and then Phoenix Sync, which is powered by Electric, is doing the stuff to keep your server in sync with the database. And that just gives you an end-to-end real-time reactive stack for live development. And so just also this is then, that's how you do LiveView. This is how you sync data out of your Phoenix router into a client for something like TanStack DB. It's just your normal like middleware pipeline. So you do authorization and any kind of stuff using plug middleware. You can reuse your existing plug middleware. And then there's a sync macro there, just like exposing, it's an ecto schema, but it can also be an ecto query. So you basically turn an ecto query into a subset of a table that you sync into the client. And then with the right to come back in, I mentioned, say, TanStack DB doing these transactional optimistic mutations. we have this writer ingest pipeline for simplifying ingesting those back into, so the writes get written back into Postgres through your API. But they can do so reusing your existing ecto schemas and change set and middleware authorization logic. So the idea is if you built like a Phoenix app and you're using APIs or LiveView or AppStamp or what have you, then you can just reuse your existing code with this pipeline and it just ingests app right into your app. And so you get this like two-way bi-directional active-active replication for local first app development. And so that's all pretty cool. And I mean, there's a bunch more details I could go through there, but to be honest, I've done that talk. So like we introduced these libraries about this time last year at Code being here in San Francisco. And then in Europe this summer at the Elixir conference, we introduced Phoenix Sync and kind of walked through this in a bunch more detail. So I kind of thought just today it might be interesting to focus on something else. You know, both these libraries are out there, so if you're interested in them, it's probably just more interesting to go read the docs than kind of like sit here and kind of listen to a talk about them. And so what I was kind of thinking about might be interested to focus on is a bit more about what it has been like for us to build Electric as a sync engine kind of dev tools product on Elixir. And both the benefits and challenges of building the system out of the Beam runtime, and also some of the opportunities that we see coming around the corner in this Elixir ecosystem that George also touched on. So there is this thing about what we do with real-time sync, where it demos really well, and it's been around a while, but it is actually it's actually very difficult to take it all the way into production. And as a result, it's never kind of become the main way of doing things. So like this kind of thing, like this is Meteor, for instance. How long has Meteor been around as a framework? Like Firebase, these things have kind of been there for ages. And as I say, they demo great. But if you, as the developer, are choosing a stack to build your application on today, do you immediately reach for this kind of real-time stuff? And it's probably not. And it's like, well, okay, the UX is better, maybe the DX is better. It's like it's declarative, you eliminate layers of the stack, it's all instant, it's local, it's reactive. But actually, it is just still complex. And so we kind of know that, like, okay, demos well, but what happens in failure scenarios? Because sockets break and messages don't get delivered and services get restarted. And then just by adding in this kind of real-time component, you either end up with something like you've got some external real-time database, or you build it into your system and it's hard to instrument, or it falls over in production, or some sort of bottleneck. And so actually, we just avoid building apps like this and go for simpler technologies that get the job done, even if they're in a way sort of suboptimal paradigm. So in a way, Sync, where you see apps like Figma, Notion, Linear, these kind of examples of apps that are built on this paradigm to offer a really good user experience, actually they've spent millions and millions of dollars of engineering to make their products that good. And so Sync, in a way, is a luxury. And what we're trying to do with Electric as a product is take the luxury and turn it into a commodity by making it just work, right? And so that's what we put nearly all of our engineering time into. We're a team of 10 people, and we are just trying to make it just work. So it scales, so it's reliable. And one of the things we talk about internally is like trying to make it a technology choice, a bit like if you were choosing, say, Redis or Postgres, where you would choose them because they're rock solid, right? If you've got a bug, it's probably in your code, it's probably not there. And so actually it's a sort of stable technology choice. And so that's what we're sort of trying to aim for. It's something that you can choose because it's simple, you can reason about it, it doesn't have these things where it comes back to bite you in the ass. And so the general view of Elixir, right, is that it's a great runtime platform language to build on that because it's reliable and it scales. In reality, I think we chose Elixir in the beginning because I'm an Elixir developer, and I liked Elixir originally just because of the language design and developer ergonomics when I tried it, where it was coming out of dynamic languages like Ruby and Python, and it was just like so much better in so many ways. And then like I hired a bunch of Elixir engineers, but we've kind of kept it because actually we do think it is the best runtime and technology for the type of product that we're building. And we do lean heavily on the beam, as you can imagine. So, very simply, right, we consume data out of Postgres. It's a logical replication connection. We do sort of filtering and mapping, and then we write it as what we call shape logs. So we have this partial replication primitive called shape. And so you might have like a transaction comes out of Postgres with a bunch of operations in it, and we're writing different operations to different shape logs. And then those shape logs are then served out to clients, and actually the sort of data delivery is kind of fanned out through a CDN. And so when we're doing that, like we're using a whole bunch of the existing Elixir and Beam primitives, so pattern matching, processes, fault tolerance, concurrency, supervision truths, etc., just as you can imagine. But it hasn't been a free lunch. So we have, the reason we spend a whole bunch of our engineering time is because we have had to spend a lot of time to be able to handle the throughput and scalability that we need to be able to just plug into whatever workload people are running for their applications. And so the kind of thing we're talking about trying to support is millions of concurrent users streaming gigabytes of data per second. And this is, these are our benchmarks demonstrating that our system can do that. But of course, again, there's a difference between having to demonstrate that in the benchmark and then running it 24/7, 365 for a variety of different real-world workloads. And so, and as we've sort of gone from like early product into more sustained use, we're actually running against those real-world workloads, and then that's been giving us a bunch of challenges to engineer against to kind of be able to deliver what we're trying to deliver. And so, our first big user was Trigger.dev. So they're a very cool, like background job, kind of durable execution platform. And so they built their real-time products on Electric. And so that was a big step up for us at the time in terms of data throughput. Like I think when they started, they were doing something like 10,000 writes per second. I think it's now like 25,000 writes per second, which is pretty much saturating the write throughput of a large Postgres instance to give a kind of sense of it. And we were consuming that into our application through a gen stage pipeline. And like it became clear that it was too slow. And we built a sort of like a pipeline where some things were being found out in parallel and some things were kind of then sort of coming together to kind of get written. And first of all, we had to kind of flush out just a bunch of bottlenecks in that code. But also, again, we were optimizing, and it came to the point where even gen stage itself, because it has overhead around like message serialization and the way it manages back pressure, and it was kind of working until it didn't work. And then we were finding kind of edge cases where we were getting like long pauses in the application. We actually went and spoke to Joseph Lynn to try and get some help with debugging it. And his advice was like strip out gen stage and just sort of build the exact process pipeline that you needed. So that was a thing where we kind of started out with these very enabling built-in primitives, but we had to kind of basically optimize them out of the flow to be able to handle throughput. And then as a kind of next thing on the storage engine, so as I say, we're kind of writing quite a lot of data into these shape logs all the time. And we started by grabbing CupDB, which is quite a mature off-the-shelf Elixir key value store. And it's very nice and very ergonomic. But again, it just didn't at all deliver the performance that we needed. So we had challenges like CPU usage. There was a bunch of kind of frequent updates happening that were really, when you dug into it, slightly unnecessary, just due to these internal data structures. Once you got above about P95, certainly up to P99, the latencies were just, in terms of transaction size, the latencies were just way too large. So whenever you have like large transactions, it just block the storage for the rest of the stuff coming in. And also it did a bunch of like specific file locking, which meant that we couldn't do strategies to either fan stuff out or have zero downtime deploys across instances. And so that's one of the things where we ended up, again, we had to basically strip it out and write a custom storage engine, and we wrote up a kind of big blog post about it, but basically we store two files. It's like a shape log and an index. And then the key things were to chunk the log and then make those immutable chunks. So that the moment that the immutable chunk was written, it could start being read. Didn't need to wait for the whole write process. And then secondly, it was then taking control of the lower level system calls to be able to batch the fsync calls to get much, much higher throughput into the disk. Obviously, you trade durability whenever you batch up the fsync calls, but we can relate that back to the durability of the ACKs or the replication log. So by kind of like going, okay, it's our custom use case, rather than making a general key value store, we were able to sort of come in and do a whole bunch of optimizations where, there's never a scenario where we can be losing knowledge data, but we can get massive speed ups. It's like 100 times faster on the kind of hop write path once we bring in a new storage engine, which was the next slide. And then we will probably need to drop down further. So there's still hot paths there, and we will go to Rust through a NIF, and it's very nice to know that the runtime is very good support for that. So that's just a nice sort of option for when we get to the point of actually needing to really go there, we can fully control like the system resources in a way that you can't quite directly from Elixir at a higher level language. And then just like recently come at it from a different viewpoint. We've had a new cloud user just over the last couple of months, and they're running a very popular AI app in the education space. A very cool team. They're growing very, very fast. They have like millions of users. They're growing like 100,000 users a month, and they have hundreds of thousands of users every day. And so their access pattern for our system turned out that they were creating, those users were, there were lots of users joining every day, and those users were all creating multiple shapes. And instead of being a lot of data throughput, it was still actually not very much data, but it was just lots and lots and lots of these objects. And that basically ended up tripping us up on things like, just in our system, we had like insert failure modes. We were doing things like wiping the shape blocks and rebuilding from Postgres to the source of truth in the event of a migration. And in some cases, we were having like algorithms to compact or garbage collect unused shapes. But when you just had so many, like we were discovering bottlenecks in the code. And this was again really related to the OTP structures. So in the beginning, it's kind of great. I'll just sort of use another process, do that in the background. But actually, like every time you introduce a stateful process like that, it just can become a bottleneck connecting the code. So again, we just have to be very careful about sort of actually trying to stay as functional as possible. Being careful about the design of the stateful processes in order to maintain performance. And other silly stuff was like, we were just copying Elixir config. So you just use kind of config, you get data structures, we were copying them into the processes, which was fine until you were getting like 1 million processes created quickly. And then suddenly the memory was ballooning, and we're trying to do like flat memory across all of this kind of whatever data sets. So yeah, those kind of, I hope that gives you a bit of a sense of like, actually that runtime, even these optimizations, we're just constantly building on the benefits of running on runtime, but it hasn't been a free lunch. And so that's been sort of some of the trade-offs where just actually we have had to get into the engineering using those primitives correctly rather than assuming you can just sort of throw Elixir around it scales. And then the other thing I wanted to touch on a bit that I mentioned with Phoenix Sync. So we've been able to integrate Electric, not just as like an external HTTP API or kind of Docker container, which is sort of normally how it's packaged, but it is an Elixir application. And so we've set it up so that you can actually have it as an embedded application as part of your Elixir application. So it's not just sort of you're composing it as a sync component into your overall stack. You can actually like have it in your app and in your runtime. So that's one of the documented modes of running Phoenix Sync, but you just do it in any Elixir application. And so you can imagine you have this stack where you have like Phoenix Sync on the back end, you have TanStackDB on the front end, and it is a very compelling way to build software. But of course, as George was talking about as well, like software is just changing so much at the moment, right? The nature of the software we're writing and the way in which we're writing the software. And you've seen with projects, for instance, like Chris McCord's work on Phoenix New, how just OTP has been a perfect agentic framework. And this sort of thing that I think we're all realizing in the Elixir space, that in other, in other worlds, you have very cool agentic frameworks, things like Master for TypeScript. But in Elixir, you just don't need it because we have the primitives built into the runtime. It's almost like if someone had been able to look ahead and design the most ideal framework for running agentic software, they would have designed OTP. But also, it's like, it's not just designing, it's the advantage of it's so battle tested. Right? This stuff has been running massive production workloads for decades, which even if you're going to go and design an agentic kind of runtime framework in another environment, you're just never going to have the same maturity level at all. And this sort of, like, I mean, Chris's kind of reports back from just building Phoenix New, or just he's like, what is an agent? It's just a gen server messaging loop, right? And it's just these low-level primitives that we're used to using in Elixir are just perfect for building agentic software. And then you have the rise of coding agents to write software, and in the Elixir ecosystem, Jose, Zach, and others have just been really pushing forward the tooling on this. So we have this tidal wave Elixir native coding agent, but also just the work like within the like usage rules effort within the packages to all have like agent stop markdown compatible markdown instructions. And so there's this thing where like these developments are potentially opening the door for much, much wider adoption of Elixir. You've had this sort of thing with like a tyranny of dynamic in software adoption, where there's only been one game in town because there's this massive ecosystem and it's JavaScript. And like when humans learn to code, they come through that door. And so everybody knows JavaScript. So the biggest community is JavaScript. So that's where all the tooling goes to. But there is this very interesting opportunity now that you're having agentic coding agents and humans are kind of moving slightly higher up the stack to go, well, what technology do those agents choose? Like, if they weren't constrained by the adoption of dynamics of people, actually, wouldn't they be able to choose the best technology for the job? And then we not here sat on the best technology for the job. So I did the silly thing earlier of, as I was knocking up these slides, I thought, it's a good question, I'm going to ask Claude. So that's just to demonstrate as a real threat just from earlier. And so my question was like, you are an expert coding agent, you can choose your own step, consider this deeply, free your mind. And you can choose your own stack. And what stack would Claude choose, right? And what did he say? Number one stack, right? For Elixir Phoenix Live. So coding agents left their own devices who love to be working in this technology. And more to the point, the last thing. And so it's like the honest truth, right? And so for us in Electric, I mean, we'll see how this plays out, but it does feel like Elixir has become a distribution opportunity. Like for us, for instance, integrating into TandStack as a way of getting like sync into mainstream development, but actually building into Elixir is maybe, you know, it's actually going to become a bigger part of the next generation of this agentic software development. And so as what we're doing with Sync evolves from keeping clients and servers in sync to keeping users and agents in sync, it's this combination of a reactive data layer with an Elixir runtime that is such a good fit for agentic systems. And just one thing to say is if you're interested in these kind of ideas around like sync and agentic software, so we're organizing a conference here in San Francisco on the 12th of November. It's called SyncConf. Check it out there. And these are the links to the project. So,
Thanks. Really interesting talk, especially the performance deep dive. Outside of the performance space, have you seen some kind of like blockers that you're alluding to at the start in terms of adoption and some of the difficulties of convincing devs to take it on? And in my own experience, when I was poking around Electric, it's like, you know, it's really appealing to have a database, and I'm just gonna like sync the database down. But then there were like some scenarios where I thought, I don't really want to put this in a database, and I kind of want to like add this into Stream and maybe have a bit of a hybrid approach. Do you see that showing up, and you know, how do you think about like fully Postgres or fully UP pieces?
Yeah, totally. So, yeah, on the first slide, yes, I mean, even just as a team, we are split between like the more product-oriented people gravitate to TypeScript, because that's kind of is genuinely still the larger market that we're sort of serving for developers, and we're kind of integrating this into front-end technologies. Whereas the sort of core team sort of started off more sort of core, like distributed systems, database, and Elixir people. So we just do have a bit of a split, like, should we build the cloud dashboard with Phoenix or on there? So we kind of carry those scars as an organization. Yeah, the kind of the hybrid stuff here with, so one of the key things with TanStack DB is, so as part of TanStack grew out of React Query, which has become TanStack Query. And so it's really, it's this awesome way of just taking a lot of boilerplate of kind of efficiently doing like REST API data loading away. And so with TanStack DB, we've worked very hard to make sure that you can have a variety of different strategies for loading data all into the same unified client store. So you can have, the storage primitive is called a collection. And then you can just like call your REST API and put the results in the collection. You can have a sync engine, and there's lots of different adapters now. There's like Electric, Trailbase, RxDB, et cetera. And so you can basically pull in data from different sources, a bit like GraphQL that gives you that sort of resolver layer to aggregate data from different sources. But you can do it as a client, and then you get this like unified live query model across them. So you do these sort of live queries to then bind data into your components from the collections, and they can query across all the collections. So actually, it's kind of that TanStack DB library or something like this was exactly one of the challenges that we found with earlier system designs in a way where sync is very cool because it like cuts out all these layers of the stack, but it also just couples you very directly between the client and the database schema. You then have to also like write into the database to get that sort of data integration. And so it's like, well, how do you do sync in a way that still supports real world hybrid data loading and incremental adoption? And that was a bunch of thinking that went into TanStack DB.
Do those goodies exist in Phoenix Sync as well, or kind of separate worlds?
Sorry, say again?
The like hybrid approach, does it exist in Phoenix Sync as well, or that's kind of at the tangent?
Yes, I mean, Phoenix Sync sort of does stuff in Phoenix on the back end, and then there is now an Igniter generator and some mixed tasks to like bootstrap, sort of add the sort of stack to have like Sync and TanStack DB as the client of your Phoenix app. But yeah, I mean, Phoenix, you could just do an XO query, you call it an API, and we haven't added a kind of storage primitive in the same way. So yeah, I mean, Phoenix Sync, yeah, it's been about sort of integrating Sync with existing Phoenix primitives and doing the difficult bit of the sort of reliable message delivery between Postgres and the backend, whereas sort of TanStack DB is very much about trying to solve that kind of the front end kind of store. And there's definitely elements of, so TanStack DB has this sort of, you could wire in data sources, has this differential data flow engine. You can kind of, it's a bit like Materialize, if you know, the kind of streaming database where you can kind of build these like real-time analytics views. And so there's a lot of use for that type of technology on the server, like people use Materialize for data analytics and increasingly for things like app building. And so maybe the differential data flow component, which is called D2TS, could be kind of pulled more into the server. And one of the things we could do at some point is do a pure Elixir implementation of that, or possibly use the existing Rust libraries to do a differential data flow implementation and work with Elixir, which would then be pretty cool. Yeah. You could have sort of live streaming ecto queries with kind of reactive data flow somehow feeding into your live.
Very cool.
Yeah. I think I'll put this again.
Sweet. Thank you so much.